The recording has started.
Good afternoon, and thank you for joining this fourth innovation webinar organized by the Smart2B project. My name is Fulvio Bernardini. I'm in charge of communication and dissemination for Smart2B, and today I will act as moderator. I will just spend a few seconds to introduce you to this webinar series. The series, that started in 2022 and will continue until November 2023, have multiple goals. First, deepen the technological challenges related to the concept of smart building. Secondly, spread information about the results of the Smart2B project, which represents, together with other similar projects funded by the European Commission, a practical answer to the challenges posed by the 2050 Sustainability Roadmap. Last but not least, the goal is also to give visibility to the European Commission's initiatives for energy transition. In the previous webinars, we had the chance to discover in detail the Smart2B project, expanding some of its technical pillars. The devices, which allow the seamless connection of complex and diversified building energy systems, and the Smart2B platform, which serves as a middle layer for the Smart2B system, enabling seamless integration, knowledge extraction, and control. In today's webinar, we will have the opportunity to explore different topics, starting from the modular and cost-effective Smart2B services. These are tools based on artificial intelligence and machine learning algorithms that can be used to analyze and prepare the building and user data collected from the devices, consolidating and optimizing the various Smart2B objectives, translating them into effective capabilities for improved occupant satisfaction, energy saving, and flexibility management. Sarnavi Mahesh will introduce this topic on behalf of Vito, that leads the development of the Smart2B services. Following, Ana Suarez will provide an overview on how INESC Coimbra is engaged in projects on energy flexibility, demand-side management, integrated management of flexible.
We do not see Fulvio now, right?
Probably lost the connection.
Okay.
Yeah, Sarnavi, maybe since Fulvio is presenting you, maybe you can start your own presentation.
Yeah.
From Smart2B side.
Yeah. I believe you can see my screens now.
Yes.
Okay, perfect. Yeah, so Smart2B services. Well, Smart2B services are mostly about modular services that integrates with the platform APIs and Smart2B devices at the lower level towards the building sides to accelerate the smart readiness of buildings, and these modular services of Smart2B take advantage of that to mainly do three things: flexibility management and demand response, cost and energy savings, and occupant comfort and satisfaction. Now, if we zoom in a bit on the services, you will see that the services are grouped into two different categories. The first one is asset management services, where most of the the goals are basically trying to reduce your energy consumption and costs, and also take into account comfort constraints or occupant satisfaction and things like that. Most of these services are modular in the sense they interface with other services with predefined, let's say, data structures and what kind of data will be exchanged. Those are agreed upon, and those are integrated through the services framework, which I'll talk towards the end of this presentation. Then in the second in the line, we have certain transversal services, which are mostly forecasting, prediction, or assessment services. Mostly they try to improve the asset management services or provide some information for user comfort and satisfaction. And in the picture, you can also see how the different services map onto the SRI key impact functionalities in a nice way. Zooming in further on each service, we'll start with the indoor comfort service. So in the indoor comfort service, we try to characterize the building mass and the building inertia or the building behavior, as you would say. We have something called we developed something called gray box modeling tool, which usually does parameter identification and also model selection. What happens in model selection is we have different models of different complexities, starting with first order, where you have one temperature that characterizes your zone temperature, and then up to 5th degree, where you have multiple different temperatures or states, temperature states, which characterizes your building. So this gray box model basically identifies parameters for different models and also does the model selection based on the data available. The inputs are usually historical weather data, mainly outdoor temperature and solar radiation. And for the internal temperature of the building, you have measurements for zone temperature, or if you have more temperature sensors, those are helpful as well. What it outputs is usually a set of parameters. I forgot to say this, but the models, the building models are usually in terms of resistance and capacitors. They're imagined as a set of resistors and capacitance in the building. That's the indoor comfort service. The indoor comfort service is independent in the sense it doesn't require other services for its functioning. It only uses a certain weather and building information, and it's a sandbox tool, basically. Doesn't need inputs from other services. Then we have the energy efficiency service. This service basically optimizes your building and asset for efficient level of energy consumption, but the workflow is based on data, in the sense that you have certain you can generate data, or you can consume historical information, weather data, and you can train using that data to develop black box building models. And then using that model, you can generate an MPC control for that particular building and asset in combination. What it does, what it requires is massive amounts of data, but once it's trained, it's you can retrain every few days or something. But once it's trained, it's quite good, and you can update the control every 15 minutes or so. One thing to add here, the energy efficiency service is also completely independent, doesn't require input from other services. Yeah, that's about it. On the flexibility service side, so this one requires input from the indoor comfort service. Forgetting the names now. From the indoor comfort service and the efficiency service as well. I'll come to that why it's required. So to start with, the flexibility service does aggregation of flexibility and disaggregation as well. For aggregation, we consider different storage devices such as EVs or buffers, and we also have buildings with their heating and cooling consumption. For electric vehicles and hot water buffers or any other storage device, it's pretty easy to quantify flexibility. You just need the energy capacities of these storage devices and the rate at which you can store energy in them, those kind of things. So what you see here in the figure here is basically the Emax and Emin values for the energy of a electric vehicle, And let's say as an example, the data requirements are arrival and departure times, and the departure energy that you can request, that the user would request from the charging setup. So what you see here, the blue line is basically you start the car starts charging as soon as possible, and that's the max charging capacity, or the energy capacity of the battery. And the lower line basically tells you how slow you can go, but still fulfill the energy request of your departure time. And then you have hot water buffers, very similar in terms of characterizing the flexibility there. You have Emin, Emax, and those correspond to certain minimum and maximum temperature values as well. Now, as I was saying before, that flexibility service depends on using the indoor comfort service and energy efficiency service information, and that will come in here. So since we need to aggregate flexibility information for a building with different assets involved in the building, we need to convert a building heating flexibility to energy or power terms. So your building has flexibility in terms of your temperature ranges, in terms of your thermal comfort constraints, which you see here. But most of your assets will have flexibility in terms of energy and power. So we need to make a conversion of this into something that consists of power and energy. So what we do is we use the building behavior model that we can obtain from the indoor comfort service. We get the baseline consumption from the energy efficiency service. And basically, we use both these information to simulate what can be the highest or the lowest amount of energy that we can still input in the building via a heat pump or a chiller without violating the temperature constraints. So that's what gives us our flexibility in terms of power and energy. And like the energy efficiency service, the flexibility is computed every 15 minutes and to stay in line with the changing baseline behavior. So the flexibility service, as I was saying before, has a flexibility aggregation and disaggregation as well. And the aggregated flexibility is then sent, or let's say, I'll come to that, is consumed by another service called the load scheduling service, which uses the flexibility information along with the baseline information to develop a load scheduling service for all the different assets, but to reduce the consumption costs, but not deviate from the efficient operation, and stays within flexibility limits to satisfy user comfort levels. Once the load scheduling service computes a profile, that can be consumed by different services to disaggregate over different assets. But we also have disaggregation on our end. In case there are no separate services to disaggregate, we can disaggregate using a priority algorithm, which takes into account your total consumption profile that's generated by the load scheduling service, and splits it over different devices according to the demand required. That's for the flexibility service. Then moving over to the load scheduling service. So the load scheduling service is actually so takes into account the flexibility information. The flexibility information is also built on top of the baseline information, which comes from the efficiency service. So it uses all of this information to develop or generate a load scheduling, optimal load schedule based on reinforcement learning. And it also takes into account price signals from NSOE website that we use. And I think that's what they use as a price signal, not static prices, but real prices from the ENSO-E website. And I haven't put their reward function here, but the reward function has two items. One of the item is the energy cost, the energy consumption, and the other is the cost. So they try to not deviate too much from the energy, which it corresponds to the baseline energy, and stay within the flexibility limits such that they can reduce the costs. So what you see here on the picture on the right, they have two different methods at the moment, this service. One is DDPG, where you can see that so this yellow and this violet or purple line is the price, and this one, the dotted top line is the flexibility upper bound, and the dotted blue line is the flexibility lower bound. And then this thick blue line is the action, and they have this orange line, which is their baseline. So when they use this DDPG based method, they have some violations here, a bit here, and then they have another version of, let's say, an improved version of DDPG where they hard constrained certain constraints. Basically, they just stop the episodic training if there is a violation. So that's how they trained the hard constraint version, to stop the training immediately and return zero reward. And that's how they did the hard constraint version. Yeah. As I said, that this the output of this service could be given over to a different service, or at least in this project, it is returned to the flexibility service to segregate over multiple devices and appliances. Then we move over to the transversal services. The first is user-centric energy profiling. This is So this so they also do demand forecasting for in general, but very specifically was also done for hot water demand. So as I was saying before, if we go here in the hot water demand, hot water buffer, we require information on buffer capacity and hot water demand. So the user-centric energy profiling forecasts hot water demand, which is used by the flexibility service to develop the flexibility graphs for a hot water buffer. The PV production is used by the load scheduling service at CERT, and that's the two major outcomes from the user-centric energy profiling. They because these kind of forecasts, especially the water demand forecast, requires heavy amount of data, they adapted transfer learning. So they developed their model using massive amounts of data from one building, but then they transferred it for a different building, tuned it quite a lot, and developed this forecast service that can forecast energy demand for different buildings. The model is retrained every 3 days, and forecasts are updated every hour. Okay.
Sorry, we're going a little bit too long.
Okay.
So if you can please speed it up. Thanks.
Yeah, I'll go quick then. Okay, so we have the air quality assessment system, which is developed at CERT, and it's mostly a recommender system. They use historical CO2 concentration and temperature and relative humidity from the sensors we have on the pilots to forecast for the next hours. And for the infectivity modeling, they use a Wells-Riley probability model, which is a pretty old probability infection model from medical science, and they use that one to model the infectivity. Just quickly in the graph, this is for office building where you assume there are 4 to 6 people, and then it produces some infectivity likelihood, and you see after certain hours there's no one in the office, so it drops to 0. So about like 10% chance of infection with that range of people in the office. Then we have the predictive maintenance and degradation for different devices. Uses zone and outdoor temperature energy consumption for different devices. It's a non-intrusive method. Tried using just to check if the cooling or the operation is the same as expected or not over different zones, and uses synthetic data to do the training. Then we have user in the loop actuation mostly for legacy devices where you cannot control them using some kind of actuator. There's this kind of interface to the building owner or the occupants where you can display the schedule and not the schedule per se, but show what to do at certain hours, and then you can also get a feedback from them. This is the performance assessment driver. Basically checks how many what kind of functionality you have, if you have smart controls or not, and then gives a number between 0 to 4, can also suggest to upgrade certain actions or measures. This is finally the services framework, where all the services basically interact through a message queuing service using the consumption and publishing approach. That's all. Sorry it took so long.
Thank you, Sarnavi. We had a technical problem before, so I'm gonna just briefly introduce Sarnavi, who specializes in mathematical optimization and control engineering, and he works at the Flemish Institute of Technological Research, VITO, since October 2021. And of course, he introduced the Smart2B services. Now, a few service information before we proceed with Anna. So given the shortness of the speeches, the Q&A session will take place at the end of the last speech. You are, however, invited to share any questions during the webinar through the chat. I will collect the questions and ask them to the speakers during the dedicated session. In case you would miss part of the event or you intend to share it with colleagues and friends, please note that the session will be recorded. The video will be made available on Smart2B's website and on YouTube in the next few days. Now it's turn for Ana Suarez to provide an overview of INESC activities in flexibility, DSM, smart grids, and smart buildings. Ana is a researcher at the Institute for Systems Engineering and Computers in Coimbra, Portugal. She is also a science manager and teaches intelligent energy management in buildings and electrical energy management at the University of Coimbra. Please, Ana.
Thank you. Just going to share my screen. Please let me know if you can see my screen. Yes? Okay. Yep. So I'm here representing INESC Coimbra, so Institute for Systems Engineering and Computers at Coimbra. I will just give a brief overview of INESC Coimbra. It is a research institution that is affiliated with the University of Coimbra, also with Institute for Systems Engineering and Computer, INESC, with only one C, and the Polytechnic Institute of Leiria. We have several research streams in our institute, but the one that is relevant for us here is the energy systems and policy. What I will bring you here, it's a brief overview of projects that we have been involved and in which we are currently involved and related to the energy transition. One thing is that important to say is that we know that a successful energy transition depends on several interrelated factors of different nature. So not only the decarbonization of key sectors like transport, building sectors, but also the part related with citizen engagement and change of energy behaviors. And here the importance of social science and humanities, the optimal integrated management of energy resources, smart use of energy, and also design and development of paths for more sustainable and resilient cities. So basically here at INESC, we work at the demand side perspective. What we are aiming is on triggering flexibility, which can be defined as changes in the normal electricity usage of end users in response to variable energy prices or any other types of incentives, or even to the own objective of self-sufficiency, maximizing integration of local generation and with benefits to the end user, and also taking profit from any energy storage systems that are installed. So working more on the part of the demand side and with the objective of triggering flexibility, there are several energy resources that can be used, such as batteries, electric vehicles. Okay, so before batteries, I'm talking about stationary batteries, electric vehicles, power to heat cannot be left aside, manageable demands, and distributed generation. What I want to bring in with this picture is that we are talking about several entities that are involved in this energy transition. We are not talking only about consumers, not only about prosumers, but we are also talking about energy communities. We have also aggregators involved. We have the DSO, we have the TSO, we have retailers, we have energy service companies. So there are several entities involved with different objectives that sometimes are quite conflicting between them. So working on these projects, what we typically do is using optimization models. This can be of two types of nature. We can talk only about multi-objective models, so in which decision makers are in general at the same level of decision and cooperation may exist to reach satisfactory decisions and solutions. And this is done by assessing the trade-offs between competing axes of evaluation. Or we can talk about different levels of decision, like the ones we use when we apply B-level optimization models. In this case, we are optimizing for problems which involve entities that don't cooperate with each other. So typically in this type of models, we talk about a leader and a follower that will, while the leader controls different variables, the follower will react to this type of signals that are given. In order just to make this a little bit more concrete, for example, let's take the situation in which we have the TSO, the DSO, and the BRP as a balanced responsible party, the aggregator, and the prosumers. We can see here the aggregator as a leader that wants to minimize the cost for any imbalanced satisfaction. And as followers, we have the prosumers that aim to maximize profit by changing their supply demands and provide flexibility based on the proposed prices that he receives from the aggregator. Another example, let's consider the relation between the DSO and the aggregator and energy communities. So while the DSO wants to minimize for the operating costs, of course, that is subject to active and reactive power balance, voltage limits, and line power constraints, the aggregator here will aim at maximizing its own profits. So now I'll just give you a brief overview of some of the projects that we currently have at INESC or projects that have been recently finished, like the one presented in this slide. Here we have the Building Hope project, building holistic optimization of consumed energy, in which INESC main role was to characterize in detail energy services consumption, perform asset management, optimize the operation across multiple energy systems, and adding building owners with contract management. The next one is ESC's grids. We were not alone in this project, also not on the previous one, of course. And the aim was to develop novel solutions and technologies for future challenges of the smart electrical power, with three main aspects: the distribution grid, the market, and the energy end user. And once again, it is here that we are acting at the part of the end user. Also, the part of behavioral demand response cannot be left aside. The B-level optimization appears here in the definition of dynamic tariffs for network use and energy. Next project, models and algorithms for automated standalone and aggregated energy management systems to enhance demand response in small and medium enterprises and residential sectors. Our focus, control energy resources that are suitable for demand response. B-level optimization models, develop B-level optimization models to study the interactions between retailers and consumers, which are endowed with home energy management systems. The part related with behavioral and organizational dimensions that influence demand response flexibility. Optimization models to characterize aggregated flexibility aim to support aggregators in defining, for example, their bids to the reserve services markets. Tools for supporting the selection of energy efficient technologies. Develop a methodologic framework to support public bodies in terms of investment planning for energy efficiency programs. Also the part of evaluating energy and carbon technologies. Optimal portfolios for multi-objective optimization modeling. Corporate power purchase agreements. That's another project that we are currently involved in, and which involves studying current models and structures, assess the risks that are related to or that appear during contract negotiation and how they affect contracts, but also evaluate drivers and barriers to the implementation of this type of purchase agreements. Another area that we've been acting it's the part related with flexibility markets. So currently in Europe, there are already aggregators acting, but the truth is that there are several barriers to their participation in flexibility markets. So one of the objectives of this project is precisely to identify those main barriers, but also to design optimization models to assist demand-side flexibility aggregators' decisions. Another area is energy flexibility in agriculture, okay? So there is also flexibility in specific sectors such as agriculture. We are currently studying several electrical loads in the agriculture sector that can be relevant for flexibility. And we are also assessing the farmers' availability and willingness to participate in energy flexibility markets and services. And this project has also pilots, which will provide us even more information on it. We've been also working with other entities, like the one presented here, in which the objective is the development of the energy transition plan for the central region of Portugal. So we are involved in the diagnosis of how the energy transition is going, the strategic options, and we are responsible for designing an action plan, guidelines, monitoring, and assessing the results. We have been also involved in the action plan for the energy efficiency for the autonomous region of Açores. So we set energy efficiency programs and actions. So we define the actions to be implemented. The actions were developed for several sectors, like the ones depicted here: industrial, residential, commerce, transportation, agriculture, fisheries, and public administration, and several energy efficiency manuals that are available on the internet were also made public. We have also had several projects with companies, such as the ones described here, like the feasibility study for the conversion of the one thermoelectric power station from coal to running on forest biomass, the characterization and evaluation of the role that energy storage equipment may play in the future electric power systems, and the consulting for the plan of the promotion of end-use efficiency of electricity. We also have international cooperation, like the studies and the projects that we did with ANEL at Brazil, the energy in the city of the future, prepayment and tariff options, and the one with EDP, evaluation of policy and actions to incentivize technological innovations in the electricity sector. And I hope that I respected time. I tried to rush a little bit.
It was perfect. Thanks, Anna. So going to the last speaker, Herman Tursche, who will introduce energy flexible buildings. Herman is a research and development embedded software engineer at Thermovolt, a company that specializes in the retrofit control of residential electric storage water heaters for energy efficiency and flexibility. Please, Herman, the floor is yours.
Okay, thank you. Let's see. No, you should see my presentation now.
Yes, we can.
Okay, thank you for inviting me for this presentation. I will. I've split up this presentation in two parts. First, I will start with a short overview of what Thermovault is doing. And after that, I will try to set up a more general discussion on what should be done to make buildings energy flexible. So to start with, the niche where Thermovault is operating is in electric water heating mostly. We also do space heating, but most of it considers electric storage water heating. Typically, these water heaters are minimally controlled. So basically, they're only trying to ensure that it's safe, that the water doesn't boil. And if there's any kind of control, it's one very common type of control on these type of water heaters is day-night control. So the devices only heat at night because in the past electricity used to be cheaper at night. Nevertheless, this could be a very useful energy asset because they consume a lot of power. There's a lot of energy storage potential in them, and it's in principle it doesn't really matter when you consume. And there are 400,000 of them just in Belgium. So that's where we started. So we retrofit water heaters with a smart controller. We optimize it in the cloud, and we control it using local devices installed into the water heater. The typical goals that we try to achieve are energy efficiency. So we, rather than heating up the vessel all the way to maximum temperature, we try to make it as cool as possible without violating comfort. That gives significant savings in radiation losses, typically 20%. We also use the water heaters for demand response services. So these are commercial services that we sell to aggregators. And we also use it for home energy management in some cases. So that's mostly self-consumption and peak shaving. We have it's a relatively young company. We've been working on it for about 5 years. It's a quite educated workforce. So we have several PhDs working on the algorithms. We have a lot of collaborations with academia in R&D projects. And recently, we've also entered a partnership with Ariston, who's also a major manufacturer of water heaters. So towards smart buildings, I see several challenges that we've also mostly seen in the context of research projects that we collaborated in, and that are also starting to pop up in practical projects. So in terms of communication, I see two main challenges. there's on the one hand, if you want a smart building, there should be some kind of communication between the devices in the building to make sure that that their behavior is interoperating. It's if you go to the if you go towards the implementation, it will become clear that it's not evident that that devices will talk to each other, especially if you consider multiple multiple vendors who have provided the devices. Everybody should agree at least on a subset of standards to be able to interoperate. And it's in the current practical environment, it's not really clear which standard you should use. So there's a whole, I think by now there are about 20 serious contenders for communicating between devices in a smart building. That's in principle, a lot of that could be fixed in software, but with the type of devices that we're using, device constraints are pushing towards limiting the choices. The usual way out is to push the problems into the cloud, so that it can be such that it can be fixed in an environment where there's more space to fix things and also to fix things afterwards. Considering the clouds, it's important to consider that it's not free. There will be costs to be able to push your data there. And it's also in terms of operations, you need to be careful because if you are not careful in your system design, costs may run out of hand, and you might also run into reliability issues. We typically take the engineering approach that in principle you should not be 100% reliable in the cloud. You should still have usable devices when you're not able to access it. In terms of objectives, that's more of application-oriented concern. It gives interesting problems where you might want to achieve different things, and often they are conflicting. So one typical thing that people nowadays want to see, at least in Belgium, is a self-consumption of energy. So when there is a PV feed in, and it's possible to consume, the device is expected to consume. But if you do that, you might sacrifice energy efficiency. We've seen that in the rest of the build project. We clearly saw that in the results that we obtained from a pilot project. So in one case, it was optimized against cost, and we saw that energy efficiency dropped significantly, but cost was still significantly lower. So that's in terms of consumer expectations, that would still be what you would expect. But in another experiment, we developed a controller that performed even better in terms of self-consumption. But in fact, it was just filling the buffer prematurely. So all the self-consumed energy was thrown away in the end due to storage loss.